because the nucleus also has moment. The neutron has moment. So the nuclear moment can affect the moment in the neutron. But there are more things. There are several isotopes. We are detecting the neutrons in an average way. So they may come with some differences coming because they hit different isotopes. Neutron wavelength is 10 to the minus 10 meters, and the length scale of strong interactions is 10 to the minus 14, 10 to the minus 15. So the neutron-nuclear interaction is, we can have it quasi-ideal, is a planar wave, so the dispersion is spherical symmetric, and we have a spherical wave function propagating. At a distance r, this is in the easiest case, this is the wave function. But B is more complex than just that. B does not depend neither on the incoming neutron direction nor on the wave vector, but it's a complex number in principle, which depends on the particular isotope, the nuclear spin, the neutron energy. As a complex number has imaginary and real part. The imaginary part is related to the neutron absorption by nuclei. So sometimes some nuclei capture the neutron. This is very much in some lanthanides and some actinides. They capture the neutron. So that changed our average. That creates a part in the B expression that is imaginary. The real part determines the scattering amplitude and can be either positive or negative. We can use this feature in biology, is very used. The problem with hydrogen and neutrons is that it has something that is called incoherent. You will see in a couple of slides. Incoherent. So it's like giving a lot of noise. If we are going to measure some properties in a protein, most of the atoms in the protein are hydrogen. So we are going to have a lot of troubles. One way is to substitute by deuterium. So when you will see some examples of magnetic lattice determination, and there is water in the crystal, so water crystallization. What I did was to substitute hydrogen by deuterium. That's easy, not very expensive in many cases. But if you want to substitute all the hydrogen atoms in a protein by deuterium, you can die before doing it. I mean, it's an impossible job. So how to do it? Well, deuterium has a scattering length different than hydrogen, and when one term is negative respect to the hydrogen. So we can measure both. There is a magic number of hydrogen atoms versus deuterium atoms that when we put them together, they cancel B. And so that's very good, because then we don't see hydrogen, but we see the rest, and that's what matters. That's what we are interested in. Coherent and incoherent scattering. B depends on nuclear spin state of each particular isotopes. So the intensity of our neutron scattering neutrons is given by this expression. We will come to this, but this expression has this product, BJBL. It has two terms when developed. One term is the coherent, and the other term is the incoherent term. This is which is very big in hydrogen, and which creates a lot of troubles when making experiments on samples that have a lot of hydrogen atoms. Coherent scattering involves two nuclear correlations, describes interference phenomena associated to the scattering of one neutron produced by all the nuclei of the sample, has a strong scattering angle dependence. So in elastic systems, we can get to the structure, or in elastic, we can get to collective modes. The incoherent scattering involves correlations between the position of one atom at T0 and the same atom position at T equal T. No interference between scattering waves and different nuclei. Incoherent scattering provides a good method to analyze atomic diffusion. It normally is an isotropic. It's an isotropic scattering. So for studies, for example, of diffusion, even for studies where you want to see rotation, ammonia rotation, for example, where you have 3 hydrogens in the with a nitrogen, it is important to go to this incoherent scattering and study it, specifically study the differences. And then you can understand diffusion problems, rotation of ammonia, of CH3 groups, some phases that occurs because some changes in the conformation, molecular conformation, difficult things like that can be studied attending to the incoherent scattering. So it's not that it's just bothering us. No, sometimes can be very important. So this is the general formula, general expression, where you have the scattering vector, the reciprocal lattice, the propagation vector, then is the spin of the incident neutron, the spin operator, the spin of the scattered neutron, and then we have the nuclear structure factor and the magnetic structure factor, which at the end, you know, because of crystallography, is what matters. Okay. This is an example. Well, this is one diffractometer in the ILL. This is a powder diffractometer. So neutrons come. This is the neutrons guide. So they comes from the reactor this way. This way. There is a monochromator here, and then a filter, the bin, the sample, and here is the multi-detector. It's called a banana of a lot of detectors. And this is what we get. We get the diffraction pattern. You are familiar with this in crystallography, in powder crystallography. Then, if you do a Rydberg analysis, you can get the nuclear structure, and these lines underneath, this is the analysis, Rydberg analysis for the magnetic structure. So here, in a single analysis, we get the nuclear and the magnetic structure. And these are corresponding to a very small impurity. This is the difference. So that indicates that we got a very good fit. And if you remember, this is one of the crystals we were using for the impurities. So we needed to study before the magnetic structure.